Hello everyone and welcome to this new class and we were discussing the canonical transformation, and as you remember, the canonical transformation is just a transformation of the coordinate in configuration space from the old one to new one, keeping into the condition that the old new coordinates, that is going to my capital Q and capital P, are going to follow the same canonical equation of motion and the modified Hamilton principle. And the advantage was that if you make somehow from the transformation the new generalized coordinate to be the cyclic in the Hamiltonian, then the calculation becomes easy. This is one of the advantage for that. Okay, so let's quickly move to we have done two type of generating function. The third type of generating function depends upon, we have already done, this is f1, which depends upon a small q, capital Q and T, and this is f2, which depends upon the small q, capital P and T. Now this is a small p, capital Q and T. Okay, so see that this is going to be this f is going to be this eqt with an added term of a small q and p. Why I'm adding a small q and p here? Because if you see this in this equation, I'm going to get p dot, I'm going to get p dot and q dot. So if I take the time derivative of this, because in equation you have a time derivative, okay, so if this is here, I have my time derivative, that is this portion, that is df3 by dt, this portion till now. So if I don't add this, so what I'm going to get is p dot and capital Q dot. Okay, so if you remember, so in here we have q dot and I have capital Q dot. So this capital Q dot and this capital Q dot I can make equal. Okay, so this is ultimately going to my dq, and this I am going to give to dq. So I can take these two terms together, but I don't have this pi dot, a small pi dot here. Okay, instead I have a small qi dot. Okay, this is small qi dot. So what I need, I don't want this a small qi, and I want a small pi. I want a small pi. So what if I add this term? So this term is going to give me that if I add some d dt of some qp here, so it's going to give me additional these four terms, that is p q dot and then qp dot. So this small q dot term with this is both sides is going to get cancelled out. So I don't want this, so this is not there, and I want this small pi, so I want this small pi, so this is there. So that's why I'm adding this. As you remember, in our type 2 derivative generating function, we subtract capital Q and capital P. So now you know that why these are adding and what these deleting are there. So once you do this, so you've multiplied by, so I'm going to equate this p dot and q dot terms here. So p dot terms, p dot is here and p dot is here. So what I'm going to get is one is df3 by pi, this is df3 by pi, this is dpi terms. So df3 by dpi, and then this is with q, so this is with q, and then if I equate this dq term, so I have dq here, so that is going to be pi and df3 by dqi. Okay, df3 by dqi, and then this Hamiltonian, this is new Hamiltonian and this is old Hamiltonian, and this is the time derivative, they are coming together equal to 0. So from this difference, for this particular generating function, the differential equations are from this pi, capital Pi is minus df by df3, and from here qi is minus df3 by dpi, and from here k is equal to h plus df3 by dt. So if you see that if your generating function is independent of time everywhere, if this part is going to be 0, and the old Hamiltonian and new Hamiltonian are going to be same if the generating function is independent of time. So let's move to the last and the fourth generating function, which depends upon a small p, capital P and the time. So now in this case, what I'm going to have is, if you see, this is my df by, this is my df4 by dt. I'm going to have time. This is p dot from here, p dot, and capital P dot, capital P dot here. But now what I have in my equation is I have q dot from here and capital Q dot from here. So I don't want both the things, because in my generating function I don't have either Q dot and a small q dot. So I want to get rid of both these equations. So what I'm going to do is, I'm going to add QIPI and subtract capital QIPI. So this QIPI is going to give me get rid of Q dot and introduce P dot. Okay, so this I want, and this is going to get rid of me from Q dot and introduce my capital Pi dot, which I want. Okay, so this is why this is add and deleted. So rest of the story is done. And then if I equate the last the equations of motion, you're going to have is this Qi and capital Qi. Okay, so now we have four equations of motion and four generating function, and corresponding to all the generating function, this is f1, f2, f3, and f4. Okay, and the corresponding to generating function, though, there are derivatives. These are the derivatives which you must remember that derivatives. Okay. Oh, so some trivial special cases you can see here, that if my f1 generating function is qi, so because corresponding to this generating function is my qi, so I can write this from here, this qi, I can write this from here, that f1, if I figure out f1 upon a small qi, so this is going to be capital Qi. So this is going to be capital Qi, which is equal to a small pi. Okay, then if we figure out f1 with respect to capital Qi, f1 with respect to capital Qi, what I'm going to get is a small qi. So a small qi is, this is minus with minus, and this is equal to the capital Pi. Okay, and then if you take second derivative, these are some trivial special cases. Or if generating function is your qp, so then from here, if you take delta f2 upon p q with respect to q, if you do, you get capital small p, that is going to be p. Okay, so what you're going to get is pi, small pi is equal to this is capital Pi. Okay, so the small pi equal to capital Pi, and then for this f2 upon pi, this small q. So this small q is equal to the capital Q. This is so this is, if you know that for this particular transformation, this small q is going into capital Q, capital Q is going to a small p. This is kind of an identity transformation. Okay, so for f2, which is qp, is a kind of identity transformation with q is equal to q. The old is going to q new, and then new momenta is going to the equal to the old momenta. So that is identity transformation. Here what you see that in this case f3, this is pi capital Q, old momenta and new generalized coordinates. So what you're getting is equation is the same identity transform, but with the negative value, that is qi going to qi, but the negative, p going to p with the negative. So this is kind of identity transformation again with the negative sign. So you must remember that this is pi qi is questions. You can be asked some questions on in your exam or session, that this a kind of transformation is identity, or an identity transformation with negative sign. Third type of transformation, in case you concentrate on this p, is pi. So what transformation, if you apply these two differential equation, what you're going to get is this capital Q is pi. So see that this is capital Q with pi same, and capital Pi to minus Qi, capital Pi to minus Qi. So if you see f1 and f4 are giving you the same transformation equations. Okay, So f1 and f4 generating function is giving you the same transformation equation, that is qq and pp. So if you add this, a transformation that leaves some of the qp pairs unchanged and interchange the rest with the sign. Okay, so that is a kind of mixed transformation, that is qp, and then that is qq2, that is f1 and f2. So if you see that mix, if you see that this is between these two transformations, qq, this is qq is going to change from q to p and p to q, and then qp, this qp f2, this f2 is going to change, it's going to remain same. Okay, so it's going to remain same. So this is a transformation, such kind of transformation, new a small q capital P plus a small q capital Q. Such transformation is doing you that the pair change of the pair and with the negative sign. Okay, and the same pair transformations. So such combinations is going to be there. These are some trivial cases: identity transformation with negative, and inverse of that, that is pi pi qi qi. So and this combi, if you take the combination f1 and f2, such sort of example exists. Okay, so but writing a generalized or general transformation, canonical transformation, is not a very easy task. That is going to be a tedious task. So so this is not easy. Okay, so either you know the generating function, what is the generating function, then you can find the transformation equations based on these generating function derivatives. What kind, if you know that what kind of f1 4 type of generating function, then you can have the transformation equations based on this function derivative. So let us try to do one example, which is the well-known harmonic oscillator example. So the Hamiltonian of the harmonic oscillator, we know that this is a p square by 2m kq square, which we know already. And if you write in terms of the omega, this is going to be p square upon m square omega square q square. So this Hamiltonian is in old coordinates, small q and small p. Okay, small q and a small p. So now we need a canonical transformation so that my Hamiltonian is going to be transformed into the new coordinate capital Q and capital P, such that you had to concentrate that while transforming that this H is going to be the cyclic in the new coordinate. That is if I transform this H from QP to some H in QP. So if I do transformation is such that, so this H is independent of this Q. Okay, so Q is my cyclic coordinate. Q needs to be cyclic. So from this if you see from this simple equation, this is p square, these are some constant, and then q square. So this gives you some certain idea, that's what we can go for. So if I write my old coordinate p in terms of some function which depends upon p, and then cos q, and q in terms of function p and sine q. So I'm going to have, we need to find this function p. Okay, because cos square q and sine square q is going to give me 1. So I'm going to, so for this function, if I'll get rid of the q from the Hamiltonian, from cos square q and sine square q. So because if I write these, if I take these two into this Hamiltonian, this is p square. If you put p square, this is going to be fp square, and then cos square q, and from here this is, if you put q square, this is fp square and sine square q. The cos square q sine square q is going to be 1. So now the Hamiltonian is going to be independent of q. That means you have already made this Hamiltonian is the cyclic of q. Okay, so q is the cyclic coordinate. So now you put it, and what you get is get rid of this q. So you just have f square p upon twice m. So q is a cyclic coordinate now. Okay, so you have to smartly choose by seeing the what kind of Hamiltonian form of the Hamiltonian in old coordinates. So let's try to use this so that I can get rid of the capital Q. So this is what is done here. So now we need to find the form of this FP that makes the transformation canonical. So if you use a generating function, let us try. This is hit and trial method. So that's why I told you that. Writing a kind of transformation equation is not easy, or generating functions. So for this particular case, it's been written and tested. There may be others also. So if you say that my generating function is like of first type, fq, which depends upon a small q and capital Q, then I can write this as, if I say this is half mv squared q square cot q. Okay, so this is my uh, generating function is f1. So f1, my generating function is depends upon q and t, and this is half m omega q square cot q. Okay, this is my generating function, and we know that the corresponding transformation equation for this f1 generating function, okay, are these. That is pi delta f upon delta qi and capital Pi delta f upon delta qi. So I'm going to use this because I am going to have the first generating function. Okay, so if I have corresponding to the first generating function, I can have this P is delta f upon delta q. So if I find delta f1 upon delta q, this is going to be my small p. So what I'm going to have is 2q. So this is going to be m omega q cot q, and the second is this is minus delta f1 upon delta q is going to be capital P, and upon this q, so this is going to be half, this is going to be half m omega q square, and cot q is going to be cosec square q with negative sign. So that negative this will becomes positive. So I'm going to have this half m omega square. So this is going to be, or I can write it, this is m omega q square, this is twice, and this is sine square q. Okay, so this is what I am going to have, this small p and capital P. So once I have a small p and capital P, so from here this is a small p is m omega q cot q. So I can write a small q as p by m omega cot q. Okay, so and from here this uh, from here also I can write this q square is equal to this twice sine square p, or you can write this is going to be from this equation, this is going to be twice p by m omega sine square q. So if q will be under root this q will be under root this sine square. So what I'm going to have is twice p m omega sine q, and then capital P will be written as capital small p. A small p is written as, in terms of p, is this is m omega cot q. Okay, so 2p m omega. So if I put is m omega cot q in place of m omega cot q, what I'm going to have is this p is m omega q cot q, m omega q cot q, and now I have already this q here is this is m omega. I can write this q in place of this q. I can write this sum over twice p m omega sine q, and then cot q I can write cos q upon sine q. So this will cancel out, and then this m omega goes inside, so it's become m omega twice p m omega, and then cos q. So now I have old coordinates, and in terms of the p coordinates, new coordinates. So if I compare with these two, these two that we have started with, this p and q, fp cos q. Okay, if I compare with this we started with this p is equal to fp cos q, and Q is equal to Fp upon this Fp upon m omega sine Q. Fp upon m omega sine Q. If we compare this with these two, okay, what we really have, so I can find out this Fp. So Fp cos Q, this cos Q is twice, is going to be twice m omega p, and similarly from this is this Fp or also with, if you figure out with sine Q, so Fp is going to be m omega p. So once you have Fp and this Hamiltonian is not depending upon Q, so it is cyclic and not depending upon time, so then you have, what you have is, if you remember, that is this k minus h minus delta f by delta t is equal to 0, because this is not dependent upon t, so this is k is equal to h. The new Hamiltonian is going to equal to the old Hamiltonian, that is f, and that is f square p by twice m, which you already have by this is f square p by twice m, the new Hamiltonian. So once we know now what is the Fp, we know what is Fp, that is twice mp omega p, so I can write it, and this is going to be omega p. Okay, so because this is Hamiltonian, the Hamiltonian is going to be the energy, so I can write this E equal to omega p, so I can have this P is E omega, and once you have P, I can find this Q dot from the new Hamiltonian, from the generalized canonical equations of this Hamiltonian, that is delta K by delta P, and this is going to be, if differentiate with respect to P, this is going to be omega. So Q dot is omega. So now you see that Q dot is my omega, so if I integrate this, dq by dt is going to be omega, so dq by, and then this Q is omega t plus phi alpha. This is alpha is some constant, can be find from some initial conditions. So my Q finally is 2p by m omega sine Q. So that is 2p by m omega sine Q. Now I know that what is P? P is E by omega. P is E by omega. So I can put this E by omega, and 2 by omega sine is there, and this Q is, because this Q is omega t plus phi, I can put it here. So I have the final form of the transformation Q and the final form of the transformation P. Okay. So this is, you started with one equation, that is these equation of that these are going to be my transformation equation P and Q, and then we made it such that the Hamiltonian is get rid of these Q by sine square cos square Q, and then it only depends upon Fp, and then finally we find out what is my Fp from this relation, and if I put this, you get your Hamiltonian. Once you get your Hamiltonian, and you know that Hamiltonian is independent of Q, the corresponding Q dot is going to be solved very easily. Okay, so this was the whole procedure to find out the generating function and transforming from Q in terms of this new coordinates Q and P, and those are here, these coordinates. If you see, these are my uh, new transformation equation between the new coordinates and old coordinates. Okay, so I think if you see, if you see the plot quickly, that these are the new old coordinates. Okay, so these are my old P, and this is my old Q in terms of E omega. This we have calculated here. Okay, and new P is E by omega, and new Q is this is omega t plus alpha. This you know, and old are these things. So you see that these are with cos and sine, so these are going to be some oscillatory terms. But in new coordinate system, because P, capital P and capital Q, this is E by omega, this is going to be a constant line, this is going to be a straight line with y equal to mx plus c type. So this is a cut at omega c, and then you have a straight line. Okay, this is the difference between when you're transforming from old coordinate to the new coordinate in configuration space. Okay, similarly you can see the phase space in phase space. If you see that these A and B are given in terms of if you see, this is my A and this is my B. Okay, and if you plot then P and Q, So because P and Q, P is E by omega and Q is simply omega, so this is going to be linear because Q is omega t plus alpha. So if you run omega t by alpha, and this is going to be a straight line, E by omega, this is constant. So important thing is that the old coordinate are on oscillating, and in the new coordinate you have a straight line. These are the straight line. So in the next class I'll end this class here, and the next class we will talk about some standard condition over which we can find the transformation is canonical or not, and then we will do certain example based on that. So for now I take your leave, and thank you very much.